First, we'll do some exercises on the topic of subgroups. For each group in the following list, find the order of the group and order of each element in the group. The first group is Z12, second is U12, third is U20. Z12, yes, yes. No, this is not power. This is Z12, so it's addition. So you have to take multiple of 5. Smallest multiple of 5, which is also a multiple of 12, because all multiples of 12 are 0 in this. Yes, because 5 and 12 are relatively prime. So smallest multiple, common multiple is 60. Actually, even in the other cases, it's the least common multiple divided by the element itself. So its order is not 60, order is 12. So it's 60 by 5. Yeah, similarly for 4 also, LCM of 4 and 12 is 12. That divided by the element 4 is 3. So order of 4 is 3. Out of 6, you have to add 2 times. 7, yeah, what about 8? It's a multiple of 12, 6 times. Yeah. And the group in part B was U of 12 under mod 12 multiplication. U of 12 is all numbers less than 12 relatively prime to 12. That would be, Yeah. Order of one is this is multiplication now, powers. Yeah. Yeah. 11 square is 121. So you can observe that U of n is not always cyclic. There is no element that generates U of 12 within U of 12 because order of 5, 7, and 11 is 2. So the subgroup generated by 5 is just 1 and 5 because its order is 2. So none of the elements generate the group. So U of 12 is not a cyclic group. Yeah. If you take U of 10, then U of 10 is 1379, and we saw this example yesterday. Um, 7 and 3 both have order equal to 4. So 7 and 3 generate U of 10. So U of n, just by knowing that, we can't, at least for now, we don't know whether it's a cyclic group or not. Then the third one was, there's nothing deeper about this. It's just, we can't make a general claim, that's all, on U of n. Yes, but converse need not be true. If it is cyclic, then it is definitely abelian. But if it is abelian, it does not have to be cyclic. Abelian group, we have, yeah, this itself is an example because modular multiplication is abelian, but it's not cyclic. Yeah, so it's only a one-way statement. U of 20 will be 1. Yeah. So order is here 8. Here this was 4. 49 you can write it as 9, right? It's a modular 20. So then 7 cube is 9 into 7. So 63, which is 3 in mod 20. And 7 power 4 is 3 into 7, which is 21, which is 1 in mod 20. Yeah. Yeah. It's 361, I think. Yeah, that is just a drill problem to understand order and order of a group and order of an element. Let Q be the group of rational numbers. Rational numbers under addition, and Q star be the group of rational numbers under multiplication. In Q, list the elements in the subgroup generated by half and do the same for Q star. First, we will see in Q under addition what will be half. Yes, yes. All multiples of half when it is addition, additive notation. So 0 times half, 1 times half, minus 1 times half, 2 times half. By 2 times half, you mean half plus half. Yeah, and so on. That's it. Then 0 times half is also included. Then we have the inverse of half and multiples of that. So the inverse of half is minus half, and then minus half plus minus half is minus 1, minus 3 by 2, so on. But in Q star, the operation is multiplication. So the subgroup generated by half will be to contain half. What about the other elements? 1 by 8 also. On the positive side, okay. Uh, and half power 0 is also included. So 1 is there. Yeah. So the same element, depending on the group and or group operation, will generate different subgroups. So the notation half doesn't have any meaning without the context of the group which it belongs to. No, this notation half doesn't mean anything if I don't tell you what group the half is coming from and what operation I am using. It only makes sense given the context of whether it is rational numbers under addition or whether it is non-zero rational numbers under multiplication. Then in Q and Q star, the same Q and Q star from question 2, find the order of each element. First, let's see Q. What is the order of, pick any element and can you tell me what the order would be? If I gave you a random element. What is the identity in Q? It is no. First of all, in Q, the operation is addition. So the identity element is 0. The order is the number such that the multiple n times a is the identity element 0. The natural number n. If when is that possible? See, the element is from rational numbers, not natural numbers. So, but we want the order of A, not n. N doesn't have any order. It's not a part of a group. When I rate n A, n is not a member of the group. It only means A plus A plus A. It's only notation, so it doesn't actually mean anything. Only in the case of real numbers and the case of numbers, this will turn out to be n simply n into A, where multiplication is defined. But if in some group multiplication is not defined, then you can't really make sense of NA in any other way than adding A n times. Yeah, yes. Yeah, but it's a natural number. Okay, then I'll just write n plus. If a is zero, then I can just write zero one time, right? One times zero is zero. So we already saw the order of the identity element is one in any group, and zero is the identity, so its order is one. But rest of the elements, by adding them, we can't get zero. So if A is not zero, then order of A has infinite order. You will never get zero by adding A again and again. That is the case in Q, where the operation was addition. In Q star, here the identity element is 1, and this operation is multiplication. Now we want A is in Q star. What is the smallest positive number n such that A power n is equal to the identity 1? But we are only dealing with rational numbers. So there's just one rational root of nth root of 1. One more element has a finite order. What is this? Minus 1 square is also 1 only, right? Square of square of minus 1 is also 1, right? Yeah. So minus 1 has order 2. And rest of the elements, like you said, uh, only if you raise it to 0, you'll get 1, but a 0 is not allowed. We are asking for the positive integer such that a power n is 1. So if a is not 1 or minus 1, then order of a is infinite, like you said. Order of 1, since 1 is the identity, its order will be 1. But unlike in the case where we saw looked at addition, where identity was the only one which had finite order, here minus 1 is an extra element that has finite order. And uh, those were just examples to get you used to the notion of order. But an interesting fact is, a general fact is that in any group, an element and its inverse have the same order. We can take the inverse, right? If a power n is 1, a power n inverse is 1 inverse, which is 1. Right? The inverse of the identity is 1. The inverse of the identity is the identity itself. By 1, we actually mean the identity element. I can write it as E. If B is equal to C, all properties of B are the same as all properties of C, right? B and C are equal. That's what it means, no? Yeah. A power n equal to E means that A power n inverse is also equal to E inverse. They're the same thing written in different ways. Yeah. We saw in one of the earlier lectures I had written that laws of exponents hold here. So for as long as m and n are integers, you can write a power m power n as a power n power m, and you can write this as a power mn. So those are the laws of exponents with a regular multiplication operation in real numbers. But the same laws will hold for groups as long as m and n are integers, and as long as you understand a power m to be a m terms, you're actually doing the group operation with m number of a's. And this holds for whether m and n are negative or positive. Doesn't matter. So yes, you can write a power n power minus 1 as a power minus 1 power n. Then a power minus 1 is a inverse. This is e. This shows that the order of a inverse is less than or equal to n. Doesn't mean that that is the order. The order is the smallest number such that for the order of A is n means n is the smallest number such that a power n is the identity. But a power 2n is also the identity then. A power n square is also the identity. So there can be other numbers such that a power that number is the identity. N is the order is only the smallest such a number. So just because A inverse power n is E doesn't mean the order of A inverse is n. It just means that the order will have to be some number that is smaller than it or equal to n. That is fine, right? So this just shows that the order of A inverse I wrote it as m, so m less than or equal to n. And we can do similar type of thing here also. Here simply A power m inverse is 1. Here I am just swapping the exponents first. Then I'll take the inverse again. But if you take the inverse twice, you will get back the original elements. So A power m is 1. This means the order of A is less than or equal to m. So n is less than or equal to n. If m is less than or equal to n and n is less than or equal to m, the only possibility is that m is equal to n. So A and A inverse have the same order. This we did only for finite case. When order of A is n and order of A inverse is m, we assume that the orders were finite. But the statement holds even when the order of A is infinite. Because if A has a finite order, then A inverse must also have a finite order. Because the order of A inverse is less than or equal to the order of A from this first part. So it's not possible for A inverse to have infinite order and A to have finite order. That's not possible. Similarly, it's not possible that A has an infinite order but A inverse has a finite order. So if one of them is has infinite order, the other must also have infinite order. Is that all right? And A and A inverse having the same order is not very surprising, but it's useful. One different one different kind of result is that for any group elements A and X, prove that XA X inverse has the same order as A. Again, like the previous statement, we assume one of them has order M and the other has order N. So if XA X inverse has order M, that means XA X inverse whole power M is the identity. What is the next step? We saw one of a result in a previous class. Uh, XA X inverse power M was what? Yeah, a simple way to If you don't remember the proof, we proved, I think, by induction, but simple way to understand is if you multiply xa x inverse twice like this, then this x inverse x will become the identity and you will be left with xa square x inverse. So again, if you multiply this x inverse and x, they'll go away and you'll get xa cube x inverse. That keeps happening again and again, and you end up with xa power m x inverse. So this means this is equal to E. Now you can multiply on the left by x inverse and multiply on the right by x. You multiply on the left by x inverse, you'll get x inverse into E. So what I am saying is x inverse x am times x is x inverse ex. But here this x inverse x will become the identity and this x inverse x will become the identity. And x inverse ex is simply x inverse x. So this becomes a power m is equal to E. So that means the order of A is less than or equal to m. That is n less than or equal to m. Similarly, if order of A is n, then a power n equals E, then x a power n x inverse is equal to x e x inverse, which is E. This we can write it as x a x inverse power n is equal to E. Which means the order of x a x inverse is less than or equal to n. That means m less than or equal to. So again, n less than or equal to m less than or equal to n, which means the only possibility is that m is equal to n. That is order of x a x inverse is equal to order of A. Okay, we'll do one last long problem and then move on to the next topic. I was supposed to do this earlier, but I forgot. This doesn't really have anything to do with subgroups. Show that any group of order less than or equal to 5 is abelian. We saw S3 is a set of bijections from 1 to 3 to 1 to 3 that had six group elements. It had six functions. F1 was the identity. F2, F3, F4 each swapped two of the elements and kept the other element fixed. Then Fi and X6 changed all the elements. Fi sent 1 to 2, 2 to 3, and 3 to 1. F6 sent 1 to 3, 2 to 1, and 3 to 2. And we saw that that group was not abelian. So we have a group of order 6 which is not abelian. So we can't make general claims about groups of order 6 or above. But we can show that if the order is less than or equal to 5, then it is abelian. And we can also kind of give the structure of the group. There's only one type of structure the group can have. So we will solve this by in a case by case basis with different orders. First, we will check order of the group is 1. Then what is the group? Yes. Is this abelian? Yeah. So this is abelian because there's just one element. So abelian condition says for all a comma b in the group, AB must be equal to BA, but both A and B are E here. So and we know that EE is simply E taken in whatever way you want it. So this is just trivially abelian. Case 2 when the order is 2, what is the group? With some symbol, let's say A, B, C, like that. Yeah. And A is not E. So now in this case, we have E is equal to EE. So E commutes with E, and A times A is simply A times A. So A commutes with A. We want AB is equal to BA for all AB in G. If you select both A and B to be the same element, then it's trivial that will simply commute. There's no problem. Only problem is when you take two different elements. So yeah, so E times A just by definition of identity is equal to A times E is equal to A. So this is what we want for abelianness. E times A is equal to A times E. So this is also abelian. Case 3, and we have E, let's say A, B, all are distinct. Then we have A is equal to EA simply by definition. We also have B is equal to EB by definition of E. Then we have to check is AB is equal to BA. How do we do that? How can you do that? Yes. AB must be one of E, A, and B, right? If AB is equal to E, then what is the issue? Yeah, yeah. So if AB is equal to E, we saw in one of the earlier problems. If we already know it is a group, and we take two group elements and their product is E. If the product is something else, then we can't say. But if the product is E, then they are the inverses of each other, and BA will also be equal to E. So if AB is equal to E, then BA equals E, and B equals A inverse. So AB is equal to BA, right? So AB equals BA. That means both are equal to E, right? AB is equal to E. Under this, if AB is equal to E, AB is equal to BA. We'll do the other case. So if AB is not E, then it has to be A or B. If AB is equal to A, then we can write AB is equal to AE. Then we can multiply by A inverse, whatever that is, on the left. Yes, means B is equal to E. Not possible because we have assumed A and B are distinct. If AB is equal to B again, then A is equal to E. This is also not possible because A, E, B must be distinct. So if E and B are distinct, then it must be the case that A and B are inverses of each other, and AB is equal to BA is equal to E. So G is abelian. Case 4, so here it's a bit more, a few more steps are required. Now, suppose we'll start with the assumption that G is not abelian and then prove that it is not possible, that there is a contradiction in every case, in every subcase. So suppose G is not abelian, then there must exist two elements such that AB is not equal to BA. Otherwise, the group would be abelian, right? So there must be at least two elements such that AB is not equal to BA. And E and B must be distinct. Yes, we'll come to that. Now, what are the possibilities for AB? Or can AB equal to E? Is AB equal to E? This is not possible, right? If AB is equal to E, then BA must be equal to E, and AB is equal to BA. But we already assume that A and B are such that AB is not equal to BA. So AB cannot be equal to E, right? Similarly, AB cannot be equal to A. If AB equal to A, B will be equal to E. That is also not possible. Because EAB must be distinct. Similarly, is AB equal to B? That is also not possible. If AB is equal to B, that would mean that A is equal to E, which is not true. So now AB is not equal to E, A or B, but it belongs to the group. So the group is what? It has E, it has A, it has B. Last element I can write it as AB. AB is not equal to any of E, A or B. So AB is a distinct element. So the four elements we already have. Whatever AB is, whatever A into B is, it can be some other element. You can call it C if that is more convenient. But whatever it is, that is the fourth element of the group. If the group is not abelian. So it must be of the form E, A, B, and AB. Correct? Now, now we will show that this group has to be abelian, which would be a contradiction. Now we see what is BA. Since B and A are elements of the group G, BA must also be an element of the group G. So BA must be one of E, A, B, or AB. If BA is equal to E, what is the problem? Then AB will be equal to E, which implies AB is equal to BA. But that's not possible because we assumed AB is not equal to BA. If BA is equal to A, then B equal to E. That is also not possible. If BA equal to B, then A equals C. That is also not possible. If BA equals AB, that is also not possible. That means that it's not a group. BA is not an element of G. So what is the conclusion? That was the initial assumption, right? We chose A and B such that BA is not equal to AB. Yes. So our assumption is incorrect. So there do not exist A and B such that AB is not equal to BA. So if the size of the group is only four, it could be in our assumption one of the things must be false. Either the group was not of size four, that is also possible, or if this situation occurs, or the group is abelian. It's one of the two. But I'm saying I'm looking at only groups of size 4. So only possibility is that the other assumption that G is not abelian is false. So G is abelian. Is that clear? What it did is we assume that it is not abelian. Then there are two elements that do not commute, that is A and B, which are such that AB is not equal to BA. Of course, it is not possible that E, A, and B are any of them are the same. They must all be distinct. Otherwise, if A is equal to E, then EB is equal to B, right? So, and if A is equal to B, AB is equal to A square, which is equal to B square, which is equal to BA. So EAB must be distinct elements such that AB is not equal to BA. We assume that. Then we show that the fourth element must then be equal to AB because AB cannot be equal to any of E, A, or B. It's distinct from E, A, and B. Then, since the group has only four elements, the group must be E, A, B, and AB. Then we check what BA must be equal to. BA cannot be equal to E, A, B, or AB from the assumptions, which would mean that BA is not in the group. But that's not possible if G is a group and A and B are elements in G, BA must be in the group. So the assumption that G is not abelian must have been false. So G is abelian. Then the group is what? What is the structure of the group? Here G was EAB. Case 2 it was EA. In case 4 what is it? It is of the form EAB with AB is equal to BA. So, so that means any group of size 4 can be written in this way. That's what it means. So E is one element. Then if you pick two distinct elements A and B, the final element must be A into B. Is that right? Or is there any other possibility? Yeah, but only possibility is if A and B are inverses of each other, then AB is equal to BA is simply E. So AB might not be the fourth element. So if A and B are inverses of each other, AB equal to E. Here on the reason AB was not equal to E was because we had assumed that AB is not equal to BA. But now we are saying that the group is abelian. So AB is equal to BA for any A and B. So it is possible that AB can be equal to BA. is equal to E. Sorry. It's possible that AB is equal to E. In that case, what will happen is you will have E, A, B, C is some other element with AB equal to E. That is A and B are inverses of E to 1. Then what you can check is what is CB. If this is equal to E, that would mean that C and B are inverses of each other, which is not possible. An element has a unique inverse, right? And we already said the A and B are inverses of each other. So CB cannot be equal to E. If CB is equal to A, that would mean that if CB equal to A, that would mean that CBA is equal to A square, but AB is equal to E is equal to BA. So C is equal to A square. That's possible. If CB is equal to B, that would mean that CBA is equal to BA is equal to E. Sorry, if CB is equal to B, then that would be, simply mean that C is equal to E, which is not possible. If CB is equal to C, that would mean that B is equal to E. That is also not possible. So there are actually two possibilities. You could have EABA square as the group. Then what would happen is you have what is B times A square? Is nothing but BA times A. But BA was equal to E. So this is E times A. So this is equal to A. So in that case, what would happen is again, if you call this as C instead of you said C is equal to E square, then this A would simply be equal to BC. So this would be CB. Right? Even in that case, you could have actually written the group as E, B, C time and CB. So yeah, that actually gives you kind of forces you back into the same structure. But we can't actually be sure. I think we'll have to try all the possibilities. I'm not sure if that is the exact structure. Actually, what I remember is, yes, for four there are actually two different structures you can have. I don't remember for five, but four there are actually two different group structures you can have. One is the cyclic group. It could be of the form, could have A square A cube. Or you could have this EAB A times B. So these are the only two structures that a group of order 4 can have. That is, later we will see isomorphisms and homomorphisms. There will, maybe I'll do it as an example that, okay, we can directly tell from here. I just showed that if uh, the group has E, A, and B, where A and B are distinct, um, the third element has to be of the form AB, and I showed that that has to happen all the time. Like even if A and B are inverses of each other, um, if AB was equal to E and we had EA BC, then A was actually equal to BC. So you could write this as EBC, and uh, that's all right, no? So you can always write G as EBC and B times C. Only thing is if B and C are not distinct, if B and C are the same element, then you couldn't write this. It wouldn't be you couldn't write E if A and B were equal, you couldn't write it as a group A square. That wouldn't make sense. So in that case, if there are only powers of A, it must be A square A cube. But if there are two distinct elements B and C in the group, then the fourth element must be BC. By two distinct elements, what I mean is if B is not a power of A, B is B is not equal to A power I for any I, then the group has the form EAB. Otherwise, the group has the form EA A square A cube. Is that okay? At least the part that it was abelian is fine, right? Yeah. So actually, the next part about the structure is um, we have still not come to isomorphisms, but uh, what it means is that any group that has order 4 will be either of this form E, A, B, and E, A, B, and the fourth element is A, B, where B is not a power of A, or it is of the form E, A square A cube. It has to be. I have not really proven it properly, but it has to be in one of the two forms. But either case, it is an abelian group. Then case 5, order of G is 5. So again, the same assumption. Suppose G is not abelian, then there must exist A comma B in G such that AB is not equal to BA. Then the group must be EA, B, AB, and BA. Is that okay? So we already showed that AB cannot be equal to E or B in the previous thing, right? If A and B are distinct and AB is not equal to BA. Under those assumptions, AB is not equal to E, or it's not equal to A, it's not equal to B, so it must be one of the elements. And we also saw that here forcing AB to be not equal to BA, we had the problem that BA was not equal to E, it was not equal to A, it was not equal to B, and it was not equal to AB. So BA must have been a different element if AB is not equal to BA. And the problem here was the group only had 4 elements. So the we said that AB must be equal to BA, but that problem is not there in case 5 because group G can have 5 elements. Since BA cannot be equal to any of these 4, we will just include BA as the fifth element. So the group is EAB, AB, and BA. Now to prove that this is actually abelian, we'll first prove a few claims. The first claim is that in this group, ABA is equal to B and BAB is equal to A. Okay, and the way we prove that is similar to all the same thing we have done previously. We'll just use closure to find out what ABA must be. So if ABA is equal to E, what is the problem? Yeah, you can write it as we'll have A inverse is BA because A times BA is equal to E. So BA and A are inverses of each other, but also ABA can be written the form AB times A. That would mean that A inverse is equal to AB. But both A, BA, there is only one unique inverse. So BA must be equal to AB, which is not possible because we have assumed that AB is not equal to BA here. So ABA cannot be equal to E. Similarly, if you check if ABA is equal to E, then AB is equal to E. That should mean that AB is equal to BA because A and B are inverses of each other, and that is also not possible. Again, if ABA is equal to B, and that is actually that would be correct. So we have to check the other things. If ABA is equal to AB, that would mean that BA is equal to or A is equal to E, right? AB times A is equal to AB, which is also not true. We assumed A and B were distinct elements. Similarly, if A times BA is equal to BA, then A again would be equal to E, which is not possible. So ABA cannot be any of four of them. That means that ABA must be equal to the leftover thing, must be equal to AB because it cannot be AB, or BA. That is correct, no? Same type of argument you can use. Similarly, you can show that BAB must be equal to A. Just by using closure. BAB must be one of these elements in the group. If you try out with all other things, with E, B, AB, or BA, you'll get contradictions. Only possibility left would be BAB is equal to A. Now we have ABA is equal to B and BAB is equal to A. Using that, we make another claim. Next claim is that A square is equal to B square. This is simple. A square is A into A, but here we have A is equal to BAB. So I can write it as A into BAB, which is nothing but ABAB. It's, okay, we'll leave it as that. Then B square is B into B, but we have B is equal to ABA. So the first B, I'll write it as ABA. Then this will also become equal to ABA. So A square is equal to B square, right? Then we say what is A square? From closure, A square is also in the group because A is in the group. G was the group E, comma A, B, AB, and BA. If A square is equal to E, then that means A is equal to E. A and A is equal to A inverse. Sorry, no, no, no. If A square is equal to A, that means A is equal to E. Because you can cancel one of the A's on both sides. Again, I wrote something. Okay, now this is correct. If A square is equal to A, then A must be E, right? Because you can multiply by A inverse on both sides. So you get A is equal to E, but that is not possible since we assumed E and A were distinct. E, A, B are all distinct. All these are distinct elements. Then A square is equal to B. If this is true, then we have a square is equal to b square that I showed here earlier. That would imply that b square is equal to b. This would imply that b is equal to e, which is again not possible. If a square is equal to ab, that would mean that a is equal to b. That's also not possible. We assumed a, b, and e are distinct. All these are distinct elements in the group. Similarly, if a square was equal to ba, that would also imply a is equal to b, multiplying on the right by a inverse, uh, both for both LHS and RHS. So this is also not possible. Then what is the only option left? Then we would have a square is equal to e, but a square is equal to b square. So a square is equal to b square is equal to e. Okay, now we have established this. Finally, here comes the contradiction. We had BAB is equal to A here. Let's shown that. Now, since BAB is equal to A, BAB times B is equal to A times B. But by associativity, I can write it as BA times B square equal to AB. But I just showed that B square is equal to E. So BA times E is equal to AB. That means that BA is equal to AB. But that directly contradicts our assumption that AB is not equal to BA. So it is not possible to have two elements A and B such that AB is not equal to BA if the group is of order 5. That all groups of order less than or equal to 5 are abelian. So yeah, this is even harder to give the structure for this. So now we can't say that it is. This is one possibility, but then yeah, this is not. Yeah, it's abelian, so this is not actually a possibility. So this is not really true. You can't have a group like this because AB is equal to BA. They are the same element. So you'll have to take this is of the form A, B, then A, B, and maybe some other C, something like that. But again, because of closure, B, C may turn out to be some other some element, and A, C might turn out to be some element of that. Yeah, can't really tell about the structure here. F6, I gave you an example of a non-abelian group. The group S3, set of bijections from 1 to 3 to 1 to 3. So to prove it is not true, then just the counter example is enough. So there might, I'm not saying that for all orders greater than 5, it is not possible to have an abelian group. That's not what it means. It just means that you can't say with guarantee that whether there is an group of there is an abelian group of or not, or whether there is a non-abelian group of some order. The only guarantee that I can give is up to order 5 that they are all abelian. For higher orders, I can give you example of abelian groups, right? You can simply take Z n with addition modulo n as the operation. That group has n elements and it is abelian. So for all orders, all finite orders and even infinite orders, you simply have the set of integers Z, which is abelian. So for all possible orders, you have abelian groups. Then one more thing you can do is this S3 that also exists for all orders greater than or equal to 3. It is non-abelian. So S2 and S1 are just very trivial examples. That is, so by Sn I mean the set of all bijections from 1 to 3n to the set 1 to 3n. So the set of all permutation. So for n is equal to 1, it's a bijection from the set containing only 1 to 1. That there's just one bijection, right? 1 goes to 1. That's all. That is abelian. So you have this set 1 to 3 up to n. That's your domain. Then the range is also 1 to 3 up to n. Then you have bijections from this set to this set. You can have n factorial bijections. You take the set of all bijections with domain and range both equal to 1 to 3 up to n. That is the set Sn. I showed you an example with n is equal to 3. For n is equal to 1, the domain is 1 and range is 1. So there's just one function, f1, which sends 1 to 1. That is abelian, similar to how we showed that in the case 1, where order of G was 1. The only element is the identity element. So here f1 is the identity element. Then in the case of n is equal to 2, you have functions bijections from 1, the set 1 comma 2 to the set 1 comma 2. Here you can have two different bijections. The first bijection is the identity. It sends 1 to 1 and 2 to 2. The second bijection is it's called the transposition, which sends 1 to 2 and 2 to 1. So there are two possible bijections, but since one of them is the identity element, this is E, this would be A, and the operation is function composition. So again, it is abelian. But for n is equal to n greater than or equal to 3, you can show that this Sn is a non-abelian group. So for each n greater than or equal to 5, I gave you an example of an abelian group, which is Zn with mod n addition, and a non-abelian group, which is Sn. But only up to 5, we can say that the group has to be abelian. Okay, I'll go to the washroom and come back in 2 minutes. Then we'll start with uh, group homomorphism. Okay, I'll come back at 8:40. Hello. Okay. We'll move on to group homomorphisms. So we'll define what a group homomorphism is. Let G and G prime be two groups. They can be the same group. No issue. A homomorphism of groups is a function. We'll denote it by a symbol phi or phi, with its domain as G and its range or codomain, not the range, the means range in according to the convention that we adopted in the preliminary section, but the phi does not have to be onto, such that phi of A times B is equal to phi of A times phi of B for all elements A and B in the domain G. So here you first do A times B. This is since A and B are elements of the group G, this A times B is actually the multiplication in G. So this is group operation of the group G. Here phi of A and phi of B are elements in G prime. They are the image of A and the image of B that are being multiplied. Both belong to G prime. So here the group operation of G, here it is group operation of G prime. Effectively, what this means is that you can multiply and apply the function phi, and that is same as applying phi to both the elements A and B and then multiplying the result. So this kind of thing is called an operation preserving function. You can, this is not a very formal definition, but you can understand the meaning, right? Well, you can say it is a homomorphism from G to G prime. That is also fine. Yes, that need. No, no, that's not, that need not. See, it's a function, right? Phi is a function. So function should be defined for all elements in its domain. So every element in G has some image in G prime. But I said it doesn't have to be onto. We never said it's an onto function, and we never said it's a one-to-one function. So the same phi, there's no inverse function for that. Yeah. If there is, then we'll give it a different name. That's a special type of homomorphism that we simply called an isomorphism. So now we are assuming that it's a homomorphism. We are not saying phi is a bijective function. We are not saying anything other than that phi preserves the operation. We don't care about what type of function it is. Then examples, the first example is it is a homomorphism from integers to integers. So how do we define it? First, we fix an integer n. Then we define for any integer a, phi of a is n times a, which in the case of integers, it is simply a plus a with n terms. And the operation in the domain and codomain is addition only. So that's why I specified that n times a. By that I mean addition of a n times. So check if this is a group homomorphism. So here, since the domain is Z under addition, you have to check phi of a plus b. Yeah. And since the range is also integers, again with addition, we have to check whether this is equal to, yeah, this, yeah, yeah. So this is a homomorphism. Of course, when you define this, you have to make sure that phi is actually a function from, is actually a function. So most of the times we'll be dealing with functions, but if you encounter this somewhere else and it's not a function, you have to must first make sure that phi is actually a function. But you can uh, rest assured that when I say it is a homomorph, when I give you something, it will at least be a function, and you only have to check whether it is a homomorphism or not, whether it is observation preserving or not. So in this case, in the first example, yes, it is a homomorph. The second example is phi from Z to the group containing 1 and minus 1. This is our G prime. GZ. And the function is defined as follows. This is okay. G prime. The operation is multiplication. Here it is addition in integers. And I define phi of an integer is equal to 1 if a is even, minus 1 if a is odd. Is phi a group homomorphism? Yeah. So if a and b are both even, a plus b is even. So phi of a plus b is equal to 1. Phi of a is equal to 1 since a is even. Phi of b is equal to 1 since b is even. So phi of a plus b is equal to 1, which is equal to 1 times 1, which is nothing but phi of a times phi of b. In this case, it is okay. Then yeah, just b1. So in all possible cases, phi of a plus b is equal to phi of a times phi of b. So we can say that phi is a homomorphism. I'll simply write homom. Okay. This is from a professor called Krishna Hanumantu. He teaches this course in NPTEL. I don't know if it is used elsewhere. In textbooks and all, they usually print out the entire thing. They don't need short forms, right? So I don't know if this is standard practice, but I'll just follow because I saw that in that course. Then the same thing, instead of saying it goes to 1 when A is even, I'll say, if I say it goes to minus 1 when A is even and 1 when A is odd. Now is phi still a homomorphism? Multiplication. Same thing as previous. So, yeah. 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 So it's not a homomorphism. To show that something is not true, simply a counterexample is, I can simply take any two even numbers. Their sum is even, so its image is minus 1, but phi of 2 times phi of 2 is minus 1 times minus 1, which is 1. It is not equal to phi of 2 plus 2. So it is not a homomorphism. Okay, we'll stop here. Tomorrow we'll see some more examples of homomorphism. Then we'll see one way in which you can easily identify. So here we still had to look for the counter example, but one easy test will tell you, of course, it's not a sufficient condition, but it will give a necessary condition for a function to be a homomorphism. From that, you can directly tell that this example 3 is not a homomorphism. Then we will look at some subgroups that arise out of our definition from homomorphism. So once you have a homomorphism from a group G to a group 3 G prime, you'll have some subgroups of G and G prime based on the homomorphism file. Look at that and we look at examples from that. If we finish that early, we'll do some problems. Um, Maybe we'll do some properties from cyclic groups if we have extra time tomorrow. All right. Good night. Bye.